Welcome to Brain Vision.
For this problem, we're going to assume that the marble is moving inside the shoebox and that the walls of the shoebox are actually 12 centimeters high. And we actually need to take into consideration what kind of potential uh, the marble would have to encounter in order to jump over a wall of the shoebox. So that means that normally, in order to get over a barrier, someone has to, or an object has to climb over the barrier physically. So if it's a vertical barrier, you have to take into consideration gravity. So we think of gravity in terms of a gravitational potential. So we need to write the mass of the object times gravitational acceleration times the height that you have to overcome. And if we assume the wall is 12 centimeters high, then this is exactly what we need to take into consideration. So in this case, we'll just write the height as y, and the height of the wall is going to be 12 centimeters. So this is something that we can also write down. And I've also written down some other given information. The acceleration of gravity, for example, is 9.8 meters per second squared. A marble would probably weigh something like 20 or have a mass of about 20 grams, which, by the way, we can convert that to kilograms, and that would be 0.020 kilograms. And we know that it has a velocity horizontally of 0.8 meters per second, which in this little drawing we can just put right here as 0.8 meters per second. So it travels towards a wall, as it's moving horizontally, and it encounters a barrier. So with this velocity, of course, the marble has a kinetic energy associated with it. Now, the calculation that we want to carry out is kind of a two-step calculation. We need the quantity C, and then we're going to need the quantity T for the transmission coefficient. But before we get those, it's really a three-step process. We need the kinetic energy, E, as well. So why don't we start by getting that, and then we'll get C, and then we'll get T. So E is equal to 1/2 mv squared, and this is going to be equal to 1/2 times 0.020 times 0.8 squared, where the mass and velocity are properly converted to SI units. And when you carry out this calculation, you get for the kinetic energy 0.0064 joules. And the next thing we need, of course, is the potential energy associated with this wall. So this is how the physical barrier of the wall translates into a potential energy. So we need the mass of the object times the acceleration of gravity times the height of the wall. And of course, if you were doing this as a homework problem, your answers could vary because, again, a you have to study a shoebox, a marble, and the values you get could be a little different. Another thing we need to specify is what L would be for this problem, and that is the thickness of the wall of a shoebox. So that might be something like 2 millimeters of thickness. And so I'm going to go ahead and just write that down. That's 2 millimeters, and that's going to be 2 times 10 to the minus 3 meters. So we'll have that piece of information here for later. So let's go ahead and proceed and get back to this calculation for the potential energy. So the mass again is 0.020. The acceleration of gravity is 9.8 meters per second squared. And the height that we said was 12 centimeters. I believe I had this written down. I did not. Oh, yes, I did. And this is converted to meters as 0.12 meters. So now what we're going to do is substitute y in right here, and we have 0.12. So the potential energy is now equal, when you carry out this multiplication, you get 0.0 0.235 joules. So obviously the kinetic energy is less than the potential energy. Now, what we want to do is get C. And the equation for C is 2mu minus E. And this is under a square root. And this is all divided by h bar, which you know h bar is h divided by 2 pi. But what we want to do next is substitute our values that we know, and this is then going to be equal to 2 times 0.020 times 0.0235, that's a 2, 35 minus 0.0064. This is all under a square root. And we have the energies in joules already. We're not working with electron volts. And of course, in the denominator, we have Planck's constant divided by 2 pi. So we have 6.626 times 10 to the minus 34 divided by 2 pi. And when you carry out this calculation, you get for C, you get 2.48. You get a very large number, 2.48 times 10 to the 32 inverse meters. So scrolling down, I'm going to leave this right here. We'll write C. We want to get T. And this is equal to e to the minus 2cl. We keep in mind that L was equal to 2 times 10 to the minus 3 meters because it was 2 millimeters. We were assuming the cardboard of the shoebox was that thick. So we have 2, or rather, let me rewrite that. E to the minus 2 times 2.48 times 10 to the 32 times 2 times 10 to the minus 3. And this, of course, is a very difficult number for a calculator. So right now we just write it as e to the minus 9.92 times 10 to the 29th. And what we can do is go a little bit further. We're really just going to end up with an estimate. But if you notice, you can write the number e as 10 to some exponent p. Now you take the log base 10 of both sides of this in order to get what p is. And this number ends up being 0.4342945. And therefore, the transmission coefficient, which is the probability of transmission, is equal to 10 to the 0.4342945 raised to the exponent of negative 9.92 times 10 to the 29th. And this comes out to equaling 10 to the negative 4.31 times 10 to the 29th, which is approximately 10 to the minus 10 to the 30th. So that's a very small probability of tunneling.